For centuries, the success of classical physics shaped not only science, but the very way human beings understood reality. The universe appeared orderly, stable, and fundamentally predictable. Every object was assumed to possess definite properties at all times. A stone had a precise position, a clear speed, and a future trajectory that could, in principle, be calculated exactly if one knew the forces acting upon it. This worldview was deeply comforting because it aligned perfectly with everyday human experience. You throw a ball, it follows a smooth path. You drop a cup, it falls to the ground. Nothing about these events feels ambiguous or uncertain, because leads to effect in a clean, continuous chain. This sense of certainty was not merely intuitive, it was mathematically formalized in classical mechanics, most famously through the work of Isaac Newton. Newton's laws described motion with extraordinary precision. Once the initial conditions of a system were known, its future could be predicted indefinitely. The universe, under this framework, resembled a vast machine operating under fixed rules. Pierre-Simon Laplace later expressed this idea in a striking way, imagining an intellect so powerful that, knowing the position and velocity of every particle in the universe, it could predict the future and reconstruct the past with absolute accuracy. In such a universe, uncertainty was not a feature of nature itself, but merely a reflection of human ignorance. This classical certainty extended beyond mechanics into other areas of physics. Light was understood as a wave moving through space, electricity and magnetism were unified through elegant equations, and thermodynamics described heat and energy with statistical reliability. Even when probability entered the picture, as in the motion of gas molecules, it was seen as a practical tool rather than a statement about reality. The molecules themselves were still assumed to have precise positions and velocities. Probability merely reflected the difficulty of tracking so many particles at once. However, as physicists began probing deeper into the structure of matter near the end of the 19th century, cracks started to appear in this seemingly perfect picture. Certain experiments produced results that classical physics could not explain. Blackbody radiation, the photoelectric effect, and atomic spectra all resisted interpretation within the old framework. Initially, these anomalies were treated as isolated problems, temporary puzzles awaiting clever fixes. Few suspected that they pointed toward a radical shift in how reality itself would need to be understood. The first major blow to classical certainty came with the realization that energy did not behave continuously at microscopic scales. Max Planck's introduction of energy quanta was meant as a mathematical trick, not a philosophical revolution. Yet it quietly undermined a key assumption of classical physics, that physical quantities could vary smoothly without restriction. Soon after, Albert Einstein showed that light itself could behave as discrete packets of energy, later called photons. This was deeply unsettling, as light had long been the clearest example of a wave phenomenon. If even light could not be neatly classified, then perhaps the classical categories of wave and particle were incomplete. As quantum theory developed, uncertainty moved from the margins to the center of physics. Werner Heisenberg formalized this shift with the uncertainty principle, demonstrating that certain pairs of physical properties, such as position and momentum, could not both be known with arbitrary precision. This was not due to experimental imperfections or measurement errors. It was a fundamental feature of nature. The more precisely one property was known, the less precise the other became. This statement struck at the heart of classical certainty. It suggested that particles do not simply have exact properties waiting to be revealed. Instead, those properties are constrained by the very structure of reality. At this stage, uncertainty was no longer just about what humans could know. It was about what could meaningfully exist. Quantum mechanics did not describe particles as having definite positions and velocities at all times. Instead, it described them using a mathematical object called a wave function, which encoded probabilities rather than certainties. The wave function did not say where a particle was, but where it might be found if a measurement were made. This marked a profound conceptual shift. Physics was no longer about describing what is, but about predicting the likelihood of different outcomes. This idea clashed violently with classical intuition. In everyday life, objects do not exist as clouds of probability. A chair is either in the room or it is not. A door is either open or closed. Classical physics reinforced this intuition by providing equations that mirrored it perfectly. Quantum mechanics, by contrast, suggested that at a fundamental level, nature does not commit to a single outcome until observation occurs. Before measurement, multiple possibilities coexist. The tension between classical certainty and quantum uncertainty is not merely technical, it is deeply philosophical. Classical physics assumes an objective reality that exists independently of observers. The universe does what it does whether or not anyone is watching. Quantum mechanics, however, seems to blur this distinction. Measurement plays a central role, and the act of observation appears to influence the outcome. This raised unsettling questions. Does reality exist in a definite state before we look, or does observation play a role in shaping what becomes real? This conflict becomes especially sharp when one tries to extend quantum principles beyond microscopic particles to everyday objects. At the scale of electrons and atoms, probabilistic behavior is undeniable. But at the scale of cats, chairs, and planets, the world appears perfectly classical. There is no visible superposition of states, no ambiguity about whether a glass is broken or intact. This divide between the quantum and classical worlds demands explanation. Why does uncertainty dominate at small scales but vanish at large ones? Early pioneers of quantum mechanics were deeply divided on how to interpret this situation. Some, like Niels Bohr, argued that quantum theory does not describe an underlying reality at all, but only the outcomes of measurements. According to this view, asking what a particle is doing when it is not being observed is meaningless. Physics should restrict itself to what can be measured and predicted. Others, including Einstein, found this deeply unsatisfactory. Einstein famously objected that he could not believe that the moon ceased to exist when no one was looking at it. To him, uncertainty was a sign of an incomplete theory, not a fundamental feature of nature. This disagreement highlights the emotional and intellectual weight of classical certainty. It was not just a scientific framework, but a worldview. It affirmed that the universe was intelligible in a direct, almost mechanical way. Quantum uncertainty threatened this picture by replacing certainty with probability and determinism with chance. Even though quantum mechanics worked extraordinarily well in practice, many physicists struggled to accept its implications fully. The discomfort arises because human intuition evolved in a world where classical physics is an excellent approximation. At human scales, quantum effects average out and become negligible. Objects consist of enormous numbers of particles, and their collective behavior suppresses quantum uncertainty. This creates the illusion that certainty is fundamental, when in fact it may be emergent. The classical world may not be the foundation of reality, but rather a stable surface arising from deeper, probabilistic laws. Understanding this requires a shift in perspective. Instead of viewing uncertainty as a failure of knowledge, quantum physics invites us to see it as a feature of existence. The universe, at its most basic level, does not follow a single predetermined script. It explores multiple possibilities simultaneously, only settling on a specific outcome when interactions force a resolution. Classical certainty, from this point of view, is not abandoned but explained as a special case. This realization sets the stage for thought experiments like Schrödinger's cat. The cat paradox does not create the tension between certainty and uncertainty, it exposes it. By applying quantum principles to a familiar, classical object, the paradox forces us to confront the uneasy coexistence of two ways of describing reality. It asks whether the boundary between classical certainty and quantum uncertainty is fundamental or merely practical. In this first keynote, the contrast between classical certainty and quantum uncertainty serves as the foundation for everything that follows. It explains why the paradox is so disturbing and why it continues to fascinate physicists and philosophers alike. The struggle is not just about equations or experiments, but about reconciling two radically different visions of the universe. One promises clarity, predictability, and objectivity. The other offers probabilities, ambiguity, and a reality that seems to wait for observation before making up its mind. This tension remains unresolved in a final sense. Modern physics uses quantum mechanics daily, building technologies that rely on its principles with extraordinary success. Yet the discomfort has not vanished. The longing for classical certainty still shapes debates about interpretation and meaning. Schrödinger's cat stands precisely at this crossroads, reminding us that the most accurate theories can still challenge our deepest assumptions about what it means for something to be real. The persistence of classical certainty in human thinking is not accidental. It is reinforced every moment by sensory experience. Our eyes deliver sharp outlines, our hands confirm solidity, and time seems to flow smoothly from past to future. Nothing in ordinary life prepares us for a universe governed by probability at its core. Because of this, when quantum uncertainty entered physics, it did not simply add new equations, it destabilized a deeply rooted mental framework. Scientists were forced to confront the possibility that the clarity they trusted was not fundamental, but approximate. One of the most unsettling aspects of quantum uncertainty is that it does not behave like randomness in everyday life. When a coin is flipped, its outcome feels random, but we still assume that the coin follows a definite trajectory, governed by precise forces. If we knew every detail of the flip, we believe we could predict the result. Quantum uncertainty is different. It does not arise from hidden complexity or lack of information. Instead, it arises even when a system is described as completely as the theory allows. This distinction is crucial, because it means that uncertainty is woven into the fabric of reality itself, not merely into our descriptions of it. This realization gradually forced physicists to abandon the idea that particles move along well-defined paths when they are not observed. In classical physics, a particle has a trajectory whether or not anyone measures it. In quantum mechanics, the notion of a trajectory becomes problematic. Between measurements, the theory does not assign a single path to a particle. Instead, it assigns a range of possible paths, all contributing to the final outcome. This idea feels almost poetic, but it is deeply counterintuitive. It suggests that nature, at its most basic level, does not behave like a collection of tiny billiard balls, but more like a shifting landscape of potentialities. The discomfort grows stronger when one realizes that quantum uncertainty is not confined to rare or exotic situations. It governs every atom in the universe. The stability of matter itself depends on it. Without quantum uncertainty, electrons would collapse into atomic nuclei, and chemistry as we know it would not exist. In this sense, uncertainty is not a flaw in nature, but a condition for complexity and structure. Classical certainty, which feels so solid and reliable, emerges only because quantum uncertainty operates in the background in a very precise way. As physicists grappled with these ideas, a crucial question emerged: where does the transition from uncertainty to certainty occur? If atoms obey quantum rules and large objects appear classical, then something must explain how one description turns into the other. Early interpretations often place this transition at the act of measurement. The measuring device, assumed to be classical, forces the quantum system into a definite state. But this explanation raised an uncomfortable problem. Measuring devices are themselves made of atoms, which should obey quantum rules as well. If everything is ultimately quantum, then where does classical certainty come from? This question exposes the fragile foundation of the classical worldview. Classical physics works extraordinarily well because it describes averages. When trillions upon trillions of particles interact, their individual uncertainties tend to cancel out. The result is a stable, predictable pattern. This does not mean that uncertainty disappears, it means that it becomes invisible. The classical world is not free from quantum effects. It is built on them. What we call certainty is, in this sense, an emergent phenomenon, not a fundamental one. This idea challenges the traditional hierarchy of physics. Instead of classical laws being the bedrock and quantum laws being a special correction, the situation is reversed. Quantum mechanics appears to be the deeper theory, with classical mechanics emerging as an approximation valid under certain conditions. This reversal is intellectually unsettling because it suggests that the clear, deterministic world we trust is a kind of illusion, or at least a simplified projection of a much stranger underlying reality. The emotional resistance to this idea should not be underestimated. Even some of the greatest physicists struggled with it throughout their lives. Einstein's objections were not merely technical, they were philosophical. He believed that a complete physical theory should describe an objective reality that exists independently of observation. To him, quantum uncertainty felt like an admission of defeat, a confession that physics had given up on describing what is actually happening. His famous remark about dice was not a casual complaint, but a statement about what he believed the universe ought to be like. Others took a different stance. They argued that insisting on classical certainty at all scales was an act of nostalgia rather than reason. Nature, they claimed, is under no obligation to conform to human intuition. If experiments consistently point toward uncertainty as a fundamental feature, then the task of physics is to accept this and move forward, even if it feels uncomfortable. From this perspective, the problem was not quantum mechanics, but our expectations. This clash of attitudes reveals something important about the nature of scientific revolutions. They do not simply replace old equations with new ones, they force a re-evaluation of what counts as explanation. Classical physics explained phenomena by telling a story about causes and effects unfolding in time. Quantum mechanics explains phenomena by providing probabilities and correlations. It tells us what outcomes to expect and how likely they are, but it remains silent about what happens in between. For many, this silence feels like an absence of understanding. Yet this apparent lack of narrative may be a reflection of the limits of human concepts. Cause and effect, position and motion, certainty and determinism are ideas shaped by macroscopic experience. At the quantum level, these concepts may no longer apply in their familiar form. Uncertainty, then, is not just a property of particles, but a signal that our intuitive categories are being pushed beyond their domain of validity. The contrast between classical certainty and quantum uncertainty also has implications beyond physics. It influences how we think about knowledge, prediction, and control. In a classical universe, the future is, in principle, fixed. If we cannot predict it, that is our fault. In a quantum universe, the future contains genuine alternatives. Even with perfect knowledge of the present, multiple outcomes remain possible. This introduces a subtle form of openness into the structure of reality itself. This openness does not mean that anything can happen. Quantum mechanics is highly constrained, its probabilities are precise, and its predictions are astonishingly accurate. What it denies is absolute certainty about individual events. Over many repetitions, patterns emerge with near-perfect reliability. Single events, however, retain an element of unpredictability. This combination of strict order and fundamental uncertainty is one of the most distinctive features of the quantum world. When this framework is applied to larger systems, the tension becomes almost unbearable to intuition. A single atom in a superposition is strange but tolerable. A cat in a superposition is absurd. And yet, if quantum mechanics is universal, the logic seems unavoidable. The discomfort we feel is a direct consequence of our attachment to classical certainty. The paradox does not arise because quantum theory is incoherent, but because our expectations are. Modern developments, such as decoherence theory, have helped clarify how classical behavior emerges from quantum systems. Interactions with the environment rapidly destroy delicate superpositions, effectively forcing systems into states that appear classical. This process does not eliminate uncertainty at a fundamental level, but it explains why we do not observe it in everyday life. The world looks certain because uncertainty is constantly being redistributed into inaccessible correlations with the environment. Still, this explanation does not fully restore classical comfort. Decoherence explains why superpositions become unobservable, but it does not explain why a specific outcome occurs. It tells us why the cat appears either alive or dead, but not why it is one rather than the other. The final step from possibility to actuality remains mysterious. This lingering gap ensures that the tension between certainty and uncertainty continues to provoke debate. What emerges from all this is a humbling lesson. Classical certainty, once regarded as the natural state of reality, turns out to be a special case. Quantum uncertainty, once seen as a flaw or limitation, reveals itself as a deeper principle. The universe is not a clockwork machine unfolding along a single path, but a system that explores multiple futures before settling into one. Our everyday experience captures only the settled outcomes, not the branching possibilities that preceded them. This realization reframes the role of imagination in physics. Imagination is no longer just a tool for visualization. It becomes essential for accepting realities that cannot be directly pictured. Schrödinger's cat, like the uncertainty principle itself, forces us to imagine a world that does not conform to classical logic. It challenges us to expand our conceptual horizons rather than retreat to familiar ground. By the end of this exploration, the contrast between classical certainty and quantum uncertainty no longer appears as a simple opposition between right and wrong. Instead, it appears as a relationship between levels of description. Certainty emerges from uncertainty, stability from fluctuation, clarity from probability. The classical world is real, but it is not fundamental. It is a surface formed by deeper, less intuitive rules. This understanding does not diminish the power of classical physics. On the contrary, it explains why it works so well within its domain. Classical certainty is not an illusion to be discarded, but a phenomenon to be explained. Quantum uncertainty provides that explanation, even if it does so at the cost of comfort. In this sense, the first keynote is not just a background idea, it is the philosophical engine driving the entire story. The moment imagination met physics was the moment certainty was forced to coexist with uncertainty. That coexistence remains one of the most profound and challenging insights ever produced by science, reshaping not only how we describe the universe, but how we understand our place within it. The second keynote focuses on the birth of a famous thought experiment, and to understand why Schrödinger's cat was conceived, it is essential to step back into the intellectual atmosphere of the early 1930s. Quantum mechanics was no longer a speculative idea, it was a highly successful theory. It explained atomic spectra, chemical bonding, and the stability of matter with remarkable precision. Young physicists embraced it enthusiastically because it worked, yet beneath this success lay deep unease. The theory produced correct numbers, but its meaning was unclear. It described reality in a way that seemed to contradict logic, intuition, and even language itself. At the center of this unease was the concept of superposition. According to quantum mechanics, a system could exist in multiple mutually exclusive states at the same time. An electron could be in different positions simultaneously, a particle could travel along different paths at once, and an atom could be both excited and unexcited until measured. Mathematically, this idea was elegant and unavoidable. Experimentally, it was confirmed again and again. Philosophically, it was explosive. The question was no longer whether quantum mechanics worked, but what it was actually saying about the world. Erwin Schrödinger was one of the architects of quantum theory itself. His wave equation was a cornerstone of the new physics, providing a powerful way to calculate how quantum systems evolve over time. Yet Schrödinger was deeply uncomfortable with how the theory was being interpreted, particularly by proponents of what later became known as the Copenhagen interpretation. This interpretation emphasized the role of measurement and suggested that quantum mechanics did not describe an objective reality, but only the probabilities of different measurement outcomes. For Schrödinger, This felt like a retreat from the original goal of physics, to describe what is happening in the world. Schrödinger was not alone in his discomfort. Many physicists sensed that something essential was missing. However, rather than rejecting quantum mechanics outright, Schrödinger chose a more subtle approach. He decided to expose the problem by pushing the theory to its logical extreme. Instead of arguing abstractly about electrons and wave functions, he translated the mathematics into a vivid, concrete scenario that anyone could understand. This decision was crucial. The power of the thought experiment lies not in technical detail, but in its ability to bridge the microscopic and macroscopic worlds. Thought experiments have a long tradition in physics. Galileo imagined falling bodies, Einstein imagined riding alongside a beam of light, and Newton imagined cannons firing projectiles around the Earth. These mental constructions allowed physicists to test ideas beyond the limits of available technology. Schrödinger followed this tradition, but with a twist. His goal was not to clarify a new idea, but to reveal a paradox. The cat experiment was designed to make people uncomfortable, to force them to confront the strange implications of a theory they were already using with confidence. In Schrödinger's scenario, every element was chosen carefully. The radioactive atom represented a genuine quantum system governed by probabilistic decay. The detector and poison mechanism served as a bridge, translating a microscopic event into a macroscopic consequence. And the cat, a familiar living being, symbolized the everyday world of definite outcomes. By placing all of these elements inside a sealed box, Schrödinger ensured that the system remained isolated from observation. According to the rules of quantum mechanics, as long as the box remained closed, the entire system had to be treated as a single quantum object. This was the crucial move. If the atom existed in a superposition of decayed and not decayed states, then the detector was also in a superposition of triggered and not triggered states. The poison vial was both broken and unbroken, and the cat, bound to this chain of events, was both alive and dead. Schrödinger did not claim that this was physically realistic or experimentally achievable. He claimed something more disturbing, that this conclusion followed directly from the accepted principles of quantum mechanics, if they were applied universally. The brilliance of the thought experiment lies in its simplicity. No advanced mathematics is required to grasp the dilemma. Anyone can imagine a cat in a box. And precisely because the image is so clear, the conclusion feels absurd. This emotional response is not a flaw, it is the point. Schrödinger wanted to show that the problem was not merely technical, but conceptual. If quantum mechanics leads us to describe a cat as both alive and dead, then something about our understanding of the theory must be incomplete or mistaken. Importantly, Schrödinger did not propose the cat to support the idea of superposition. He introduced it as a criticism. Over time, popular accounts have sometimes inverted this intention, treating the cat as a demonstration of quantum weirdness rather than a challenge to it. In its original context, the thought experiment was a warning sign. It highlighted the danger of applying quantum concepts without clear interpretive boundaries. The timing of the thought experiment was also significant. In 1935, the same year Schrödinger published his cat paradox, Einstein, along with Podolsky and Rosen, presented their own challenge to quantum mechanics, now known as the EPR paradox. Both critiques targeted the same issue, whether quantum mechanics provided a complete description of reality. The fact that these concerns emerged simultaneously from different thinkers underscores how widespread the discomfort was. Schrödinger's cat addressed a different angle than EPR. While EPR focused on entanglement and non-local correlations between distant particles, the cat paradox focused on scale. It asked whether the rules governing atoms could truly apply to macroscopic objects. This question strikes at the heart of our understanding of reality, because it blurs the boundary between the microscopic and the everyday. If there is no clear cutoff between quantum and classical, then where does the world we experience come from? The thought experiment also reveals something subtle about the role of language in physics. Words like alive and dead, on and off, broken and intact are classical categories. They assume exclusivity. Something cannot be both at once. Quantum mechanics, however, uses a mathematical language that allows combinations of states. Translating this mathematical structure into everyday language produces paradoxes. Schrödinger's cat dramatizes this translation problem. It shows how the mathematical success of a theory can outpace our ability to describe its implications coherently. Another reason the cat thought experiment gained such prominence is that it exposed a tension between realism and operationalism. Realism assumes that physical systems possess properties independent of measurement. Operationalism focuses only on the outcomes of measurements themselves. Schrödinger's discomfort stemmed from the feeling that quantum mechanics, as interpreted by many of his contemporaries, abandoned realism too quickly. The cat paradox forces this issue into the open. Is the cat really in a definite state before the box is opened, or does that question have no meaning within the theory? By choosing a living creature rather than an inanimate object, Schrödinger also heightened the emotional impact of the paradox. Life and death are not abstract properties. They carry moral and existential weight. This choice was deliberate. It ensured that the paradox would not remain confined to technical debates among specialists. It invited philosophers, and eventually the broader public, into the conversation. The cat became a symbol precisely because it touched something deeper than physics. Over time, the thought experiment took on a life of its own. As quantum mechanics continued to prove successful, attention shifted from Schrödinger's original criticism to the puzzle itself. Physicists began asking how the paradox could be resolved rather than whether quantum mechanics should be rejected. This shift transformed the cat from a critique into a catalyst. It inspired decades of research into measurement theory, decoherence, and the foundations of quantum mechanics. Yet the original motivation should not be forgotten. Schrödinger did not believe that cats actually exist in superposed states. He believed that the theory, as interpreted, was being stretched beyond its legitimate domain. The thought experiment was meant to highlight the need for clearer principles, not to celebrate mystery for its own sake. In this sense, the cat represents a moment of intellectual honesty. It reflects a refusal to ignore uncomfortable implications simply because a theory is successful. The birth of Schrödinger's cat also illustrates the power of imagination in scientific progress. Imagination is often associated with speculation, but here it serves a critical function. By imagining an impossible situation, Schrödinger revealed a real problem. The paradox does not depend on experimental verification to be meaningful. Its force comes from logical consistency. If a theory leads to conclusions that contradict our most basic understanding of reality, then those conclusions demand explanation. This approach has shaped how foundational questions are addressed in physics ever since. Thought experiments remain central to debates about black holes, time travel, and the nature of information. Schrödinger's cat stands as one of the most successful examples of this method. It shows that sometimes to understand a theory, one must imagine its consequences in extreme and even absurd contexts. At its core, the birth of this thought experiment marks a turning point in the philosophy of physics. It signals a shift from asking only whether a theory works to asking what it means. Quantum mechanics forced physicists to confront the possibility that reality itself might not align with classical logic. Schrödinger's cat was born out of this confrontation. It was not a whimsical invention, but a serious intellectual challenge, crafted to expose the unresolved tension at the heart of modern physics. In this way, the cat did more than illustrate a problem. It preserved it. By giving the paradox a memorable form, Schrödinger ensured that it could not be easily ignored or forgotten. Long after the original debates have faded, the image of the cat in the box continues to provoke questions about measurement, reality, and the limits of scientific description. The thought experiment was born from discomfort, but it endures because that discomfort remains unresolved. As the thought experiment spread beyond its original context, its meaning began to evolve in ways Schrödinger himself might not have anticipated. What started as a pointed critique slowly transformed into a central symbol of quantum mechanics itself. This transformation reveals much about how scientific ideas develop once they leave the hands of their creators. The cat became a vessel into which different interpretations, anxieties, and hopes about quantum theory were poured. One reason for this evolution was that Schrödinger's challenge arrived at a moment when physics lacked a clear interpretive consensus. Quantum mechanics had multiple competing interpretations, none of which could claim decisive experimental confirmation over the others. The Copenhagen interpretation dominated teaching and practice, largely because it provided clear rules for calculation and prediction. Yet it left foundational questions unanswered. Schrödinger's cat dramatized precisely those unanswered questions, making it impossible to pretend they were merely philosophical distractions. As younger physicists encountered the paradox, many did not see it as an argument against quantum mechanics, but as an invitation to rethink measurement and observation. The cat shifted from being a warning sign to being a puzzle to be solved. This shift marked an important change in attitude. Instead of asking whether quantum mechanics should be replaced, physicists increasingly asked how its strange implications could be reconciled with the appearance of a classical world. This change was influenced by historical context. The mid-20th century saw rapid technological and experimental advances. Nuclear physics, solid-state physics, and later quantum electronics all relied on quantum theory. Its success in building real-world devices made outright rejection seem implausible. As a result, the paradox of the cat became less a threat and more a challenge. If the theory works so well, then the paradox must be telling us something profound rather than signaling failure. The thought experiment also gained power because it exposed a subtle ambiguity in the concept of measurement. In everyday language, measurement seems straightforward. You look, you check, you record. In quantum mechanics, measurement is a special process that changes the system being measured. Schrödinger's box isolates the system from observation, forcing us to confront what measurement really means. Does opening the box cause the outcome, or does it merely reveal it? The experiment does not answer this question, but it ensures that it cannot be ignored. As discussions deepened, some physicists proposed that the problem lay not with quantum mechanics itself, but with the assumption that the wave function represents physical reality. If the wave function is merely a tool for calculating probabilities, then the idea of a cat being both alive and dead loses its force. In this view, the wave function does not describe what exists, but what we can expect to observe. The cat is always either alive or dead. The superposition reflects our ignorance, not the cat's condition. Others found this response unsatisfying. If the wave function is only a bookkeeping device, then why does it evolve according to precise physical laws? Why does interference occur, producing effects that depend on the reality of superposition? Schrödinger's cat thus became a battleground between epistemic and ontic views of quantum states. Is the wave function about knowledge or about being? The paradox also forced physicists to confront scale in a new way. Classical physics had long assumed a smooth continuity from small to large. Schrödinger's thought experiment questioned this assumption. It suggested that if quantum rules apply at the atomic level, then in principle they should apply at all levels. The apparent absence of macroscopic superpositions demanded explanation. This problem would later motivate the development of decoherence theory, but at the time it remained deeply mysterious. As the decades passed, the cat entered popular culture, often stripped of its original critical intent. It became a shorthand for quantum weirdness, a playful illustration of paradox rather than a serious philosophical challenge. While this popularization helped spread interest in quantum physics, it also risked oversimplification. The image of a cat that is somehow magically alive and dead at the same time can obscure the careful logic behind the thought experiment. Yet even in simplified form, the cat retained its power. It made abstract ideas accessible. It provided a concrete image for discussions about probability, observation, and reality. This accessibility ensured its survival across generations of physicists and students. Few other thought experiments have achieved such cultural longevity, precisely because few managed to connect technical issues with everyday concepts so effectively. Within the scientific community, the cat also influenced how new interpretations of quantum mechanics were received. When Hugh Everett proposed the many worlds interpretation in the 1950s, the cat paradox took on a new role. Instead of being both alive and dead in one world, the cat was alive in one branch of the universe and dead in another. Measurement did not collapse the wave function, it caused the observer to become correlated with different outcomes. In this framework, the paradox dissolves, but at the cost of accepting an enormous multiplicity of realities. Other interpretations offered different resolutions. Some introduced hidden variables, suggesting that quantum mechanics is incomplete and that deeper deterministic processes underlie apparent randomness. Others modified the theory itself, proposing objective collapse mechanisms that prevent macroscopic superpositions from persisting. Each of these approaches can be seen as a response to the challenge first articulated by Schrödinger's cat. The thought experiment became a benchmark against which interpretations were tested. What makes the birth of the cat particularly significant is that it illustrates how criticism can be productive. Schrödinger did not intend to provide a solution, he intended to reveal a problem. That revelation sparked decades of creative work. The paradox functioned like a stress test, probing the conceptual limits of quantum mechanics. By pushing the theory into an uncomfortable corner, it exposed assumptions that might otherwise have gone unnoticed. The cat also highlights the importance of clarity in scientific communication. Schrödinger deliberately avoided technical jargon, he used a story instead of equations. This choice ensured that the issue could be discussed not only among specialists, but across disciplinary boundaries. Philosophers of science took up the paradox as a serious topic, exploring its implications for realism, causality, and the nature of explanation. The dialogue between physics and philosophy was strengthened by this shared reference point. Another lasting impact of the thought experiment is its role in shaping how scientists think about limits. Schrödinger's cat reminds us that a theory's success does not guarantee its completeness. A model can predict outcomes accurately while leaving deep questions unanswered. This insight encourages intellectual humility. It suggests that scientific progress involves not only refining calculations, but also questioning foundational assumptions. The endurance of the cat paradox also reflects a broader pattern in the history of science. Some of the most important ideas arise not from direct observation, but from reflection on existing theories. The cat was never meant to be built or tested. Its value lies in logical consistency rather than empirical data. This challenges the notion that science advances only through experiments. Conceptual analysis plays an equally vital role. In modern discussions, Schrödinger's cat often serves as an entry point into debates about quantum information and computation. Technologies that manipulate superpositions and entanglement bring the paradox closer to practical reality. While no one places cats in quantum boxes, experiments now routinely create superpositions of increasingly large systems. Each such experiment echoes the original challenge: how far can quantum behavior be extended before classical certainty reasserts itself? Despite these advances, the fundamental question raised by the birth of the thought experiment remains unresolved. Does quantum mechanics describe reality itself, or only our interactions with it? Is the boundary between quantum and classical fundamental or emergent? Schrödinger's cat does not answer these questions, but it ensures that they remain central. Looking back, the creation of the cat can be seen as an act of intellectual courage. Schrödinger chose to confront the implications of his own theory rather than ignore them. He acknowledged that mathematical success does not automatically translate into conceptual clarity. By doing so, he set an example that continues to resonate. Science advances not only through confidence, but through doubt. The birth of this famous thought experiment thus marks a moment when imagination was used not to escape reality, but to interrogate it. By imagining an impossible scenario, Schrödinger illuminated a very real problem. The cat endures because the tension it reveals has not been resolved. It stands as a reminder that even our most powerful theories can challenge our deepest intuitions, and that facing those challenges is an essential part of understanding the universe. The idea of superposition and probability lies at the very heart of quantum physics, and understanding it requires letting go of habits of thought shaped by everyday experience. In the classical world, objects are always in one definite state. A light is either on or off. A coin is either heads or tails. Even when we are uncertain, we assume that the object itself is not. Our ignorance does not affect the object's reality. Quantum physics introduces a radically different picture. At the microscopic level, systems do not merely hide their states from us, they genuinely exist in combinations of possibilities until a measurement takes place. Superposition is the formal expression of this idea. In quantum mechanics, the state of a system is described by a wave function, a mathematical entity that encodes all the possible outcomes of a measurement and their associated probabilities. Crucially, the wave function allows multiple states to coexist. A particle can be in several positions at once, an atom can be in multiple energy states simultaneously, and a photon can take more than one path at the same time. These are not metaphors or approximations. They are literal consequences of the theory, confirmed repeatedly by experiment. What makes superposition so difficult to grasp is that it has no true analog in classical physics. In classical probability, uncertainty reflects incomplete information. When you roll a die, you do not know which face will land up, but you assume that the die already has a definite orientation at every moment of its motion. The probability reflects your lack of knowledge, not the die's physical state. Quantum probability is fundamentally different. Before measurement, the system does not possess a single definite value for the property being measured. The probability does not describe ignorance of reality, it describes reality itself. This distinction becomes clear when quantum systems interfere with themselves. Experiments such as the double-slit experiment demonstrate that particles behave as if they pass through multiple paths simultaneously. When not observed, a single particle produces an interference pattern, a signature of wave-like behavior arising from superposition. When observed, that interference disappears, and the particle behaves as if it chose a single path. This behavior cannot be explained by assuming that the particle always had a definite path. The pattern emerges precisely because the particle exists in a superposition of paths. Probability enters the picture at the moment of measurement. Quantum mechanics does not predict which outcome will occur in an individual measurement. Instead, it assigns probabilities to each possible outcome. These probabilities are not arbitrary. They are determined by the structure of the wave function and evolve in time according to precise mathematical rules. When measurements are repeated many times on identical systems, the outcomes follow these predicted probabilities with remarkable accuracy. The theory is therefore both indeterminate and exact, unpredictable in individual events, but perfectly reliable in statistical patterns. This dual character challenges classical expectations about explanation. In classical physics, explanation often means tracing a chain of causes leading to a specific effect. In quantum physics, explanation often stops at probability. The theory tells us how likely different outcomes are, but it does not provide a deeper reason for why a particular outcome occurs in a given instance. For many, this feels incomplete, as though something essential is missing. Yet decades of experimental evidence suggest that this probabilistic structure is not a temporary limitation, but a fundamental feature of nature. The superposition principle also implies that quantum states can be added together to form new states. This mathematical freedom has profound physical consequences. It allows quantum systems to exhibit behaviors that have no classical counterpart, such as entanglement, where the states of multiple particles become inseparably linked. In entangled systems, the superposition applies not just to individual particles, but to the system as a whole. The probabilities of outcomes for one particle depend on the outcomes for another, even when they are separated by large distances. Understanding superposition requires abandoning the idea that physical properties must have definite values at all times. Instead, properties become contextual. They take on definite values only in relation to specific measurements. This does not mean that anything goes or that reality is arbitrary. The possible outcomes and their probabilities are strictly constrained by the theory. What changes is the role of definiteness. It is no longer a permanent feature of the system, but an event that occurs during measurement. The mathematical formalism of quantum mechanics reflects this shift. The wave function evolves smoothly and deterministically according to Schrödinger's equation. In this sense, there is no randomness in the evolution of the wave function itself. Randomness enters only when a measurement is made. At that moment, the wave function appears to collapse, producing a single outcome from among the many possibilities encoded in the superposition. This apparent collapse is not described by the same deterministic equations, creating one of the central puzzles of quantum theory. Probability, in this context, is not a secondary concept. It is the primary link between theory and observation. The wave function does not tell us what will happen, it tells us what can happen and how likely each possibility is. This probabilistic structure has been tested with extraordinary precision. Experiments involving atomic transitions, particle decays, and quantum interference have confirmed quantum probabilities to many decimal places. No alternative deterministic theory has matched this success without introducing additional complexities or assumptions. The philosophical implications of this probabilistic framework are profound. It challenges the idea that the universe unfolds along a single, predetermined path. Instead, the future appears open, branching into multiple possibilities until one is realized through interaction. This openness does not imply chaos. Quantum probabilities are tightly governed by mathematical rules, but it does imply that the universe does not commit to a single outcome in advance. This idea becomes especially striking when superposition is extended to larger systems. At the level of atoms and molecules, superposition is experimentally routine. Scientists can prepare atoms in superpositions of energy states and observe interference effects with large molecules. Each such experiment reinforces the idea that superposition is not limited to an abstract mathematical realm, but is a real physical phenomenon. The difficulty lies not in accepting superposition at small scales, but in understanding why it does not manifest clearly at larger ones. Probability also reshapes the notion of causality. In classical physics, causes lead inevitably to effects. In quantum physics, causes lead to distributions of possible effects. The connection between cause and effect becomes statistical rather than deterministic. This does not eliminate causality, but it changes its character. Causes constrain what can happen and how likely it is, rather than dictating a single outcome. This statistical causality can feel unsatisfying, but it has proven extraordinarily powerful. Quantum probabilities allow precise predictions about averages and correlations, even when individual events remain unpredictable. Technologies such as lasers, semiconductors, and quantum sensors rely on this statistical reliability. They work not despite quantum uncertainty, but because of it. Superposition and probability are not obstacles to control, they are resources. The discomfort with probability often arises from a desire for hidden certainty. It is tempting to imagine that quantum probabilities reflect unknown variables that, if discovered, would restore determinism. This idea has motivated many alternative theories. However, rigorous results such as Bell's theorem have shown that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. These results suggest that quantum probability cannot be dismissed as mere ignorance without giving up other deeply held assumptions about the world. Superposition also challenges the classical notion of identity. In a superposition, a system does not have a single, well-defined state. Instead, It embodies several mutually exclusive possibilities at once. This does not mean that the system is vague or ill-defined. On the contrary, the superposition is precisely defined mathematically. What is challenged is the assumption that physical reality must always align with classical categories. The role of probability becomes clearer when one considers repeated measurements. If a quantum system is prepared in the same superposition many times, the outcomes of measurements will vary, but their frequencies will converge to the predicted probabilities. This statistical stability gives quantum mechanics its empirical power. It also highlights the difference between individual events and collective behavior. While single events are unpredictable, ensembles reveal order. This interplay between unpredictability and order is one of the most striking features of quantum physics. It suggests that randomness and structure are not opposites, but complementary aspects of reality. Superposition generates possibilities, probability organizes them, and measurement selects one outcome. The process is neither chaotic nor fully determined. It occupies a middle ground that challenges classical intuitions. The difficulty of accepting this framework often stems from language. Words like either and or, true and false, exist and does not exist are deeply ingrained. Superposition forces us to use and where we expect either. A particle can be here and there, a state can be this and that. This linguistic strain reflects a deeper conceptual strain. Our everyday concepts evolved to describe a macroscopic world where superposition is effectively hidden. Applying them directly to the quantum world leads to confusion. Nevertheless, superposition and probability have become indispensable tools for understanding nature. They allow physicists to describe phenomena that would otherwise remain inexplicable. From the stability of atoms to the behavior of materials and the flow of information at the quantum level, these ideas provide a coherent and predictive framework. Their success forces us to reconsider what we mean by explanation and understanding. As this keynote develops, superposition and probability emerge not as optional interpretations, but as unavoidable features of the quantum description of reality. They represent a departure from classical certainty, but not a retreat into vagueness. Instead, they offer a new kind of precision, one that trades absolute predictability for statistical exactness. Accepting this trade requires imagination, humility, and a willingness to revise deeply held assumptions about how the world works. In the context of Schrödinger's cat, superposition and probability take on dramatic significance. The cat paradox exists precisely because quantum superposition, combined with probabilistic measurement, seems to collide with everyday notions of reality. Understanding these concepts at the microscopic level is therefore essential for grasping why the paradox is so troubling and why it continues to provoke debate. Superposition and probability are not just abstract ideas, they are the conceptual engine driving one of the deepest challenges in modern physics. As superposition and probability are pushed further, their implications begin to reshape not only physics but the very idea of what it means for something to exist. In classical thinking, existence is binary. An object either has a property or it does not. A particle is either here or there, moving or at rest. Quantum mechanics undermines this binary logic by introducing a layered notion of existence. A system in superposition does not lack reality, rather, its reality is distributed across multiple possibilities. Each possibility is real in a precise mathematical sense, even if only one becomes actualized in experience. This distributed reality is deeply unsettling because it resists visualization. Classical intuition relies on pictures, trajectories, paths, positions. Quantum superposition refuses to be reduced to a single picture. Instead, it is captured by abstract mathematics. The wave function is not a physical wave in space like a water wave. It is a mathematical object that encodes probabilities. Attempts to imagine it as a physical ripple often lead to misunderstanding. The difficulty here is not a failure of imagination, but a sign that quantum reality operates beyond the categories imagination was shaped to handle. Probability, in this framework, takes on an ontological weight that classical probability never had. It is not merely a statement about what we know, but about what can be said to exist prior to measurement. Each possible outcome in a superposition carries a probability amplitude, and these amplitudes can interfere with one another. This interference is crucial. It shows that probabilities in quantum mechanics are not independent options waiting in line. They combine, cancel, and reinforce each other in ways that have observable consequences. This behavior has no counterpart in classical probability theory. The interference of probabilities reveals that quantum superposition is not just about uncertainty, but about structure. The wave function contains phase information that determines how probabilities interact. Two possibilities can enhance each other or negate each other entirely. This means that the outcomes we observe are shaped not only by which possibilities exist, but by how they relate to one another. Reality, at the quantum level, is relational before it is actual. This relational aspect becomes especially striking in composite systems. When two or more quantum systems interact, their superpositions can become entangled. In an entangled state, the system cannot be described as a collection of independent parts. The probabilities apply only to the system as a whole. Measuring one part immediately constrains the possible outcomes of the other, not because of a signal or force, but because the superposition itself encodes a joint structure. Probability here describes correlations rather than isolated events. The existence of such correlations forces a rethinking of individuality. In classical physics, objects are separate entities with their own properties. In quantum physics, individuality can dissolve into collective states. A particle's properties may not belong to it alone, but to the system it is part of. This challenges deeply ingrained notions of separateness and autonomy. Superposition and probability together suggest that reality is less like a collection of independent things and more like a network of interdependent possibilities. This perspective also changes how time is understood. In classical physics, the future is determined by the present. In quantum physics, the future is constrained but not fixed. Superposition allows multiple futures to coexist as possibilities. Probability governs how likely each future is to become actual. Measurement then selects one path, but that selection is not written into the past. This introduces a genuine openness into the structure of time. The future is not merely unknown, it is not yet decided. Such openness raises questions about causation. If outcomes are not predetermined, what role do causes play? Quantum mechanics answers this by redefining causation in probabilistic terms. Causes shape the space of possibilities and their probabilities, but they do not dictate a single outcome. This does not eliminate causality, it transforms it. Causation becomes a matter of influence rather than command. The present influences the future by shaping probabilities, not by enforcing certainties. This shift has profound implications for explanation. In the classical worldview, to explain an event is to show why it had to happen. In the quantum worldview, to explain an event is to show why it was likely to happen. This difference can feel unsatisfying because it leaves room for alternatives that did not occur. Yet this openness is not a weakness. It reflects the fact that the universe, at its most fundamental level, is not a single unfolding story but a branching structure of potential stories. Superposition also reframes the meaning of measurement. Measurement is not a passive act of discovery, as it is in classical physics. It is an interaction that transforms possibilities into outcomes. Before measurement, the system is described by a superposition of states. After measurement, the system is found in a definite state. The transition between these descriptions is abrupt and not captured by the smooth evolution of the wave function. This tension lies at the heart of the measurement problem. Probability enters this transition as a rule governing outcomes, but not as an explanation of the transition itself. Quantum mechanics tells us how likely each outcome is, but it does not tell us why one outcome occurs rather than another in a particular instance. This gap has motivated countless interpretations and debates. Some attempt to explain collapse as a physical process, others deny its reality altogether, and still others treat it as a subjective update of information. Each approach grapples with the same core issue: how superposition gives way to certainty. Despite this unresolved tension, superposition and probability have proven indispensable in practice. They enable calculations of astonishing accuracy. Quantum probabilities are not vague guesses, they are precise numerical predictions. In experiments, deviations from these predictions are vanishingly small. This reliability gives quantum mechanics its authority, even as its interpretation remains contested. The theory's success forces acceptance of its core principles, regardless of philosophical discomfort. The practical power of superposition becomes especially clear in modern quantum technologies. Quantum computing exploits superposition to process information in ways impossible for classical computers. A quantum bit can exist in a superposition of states, allowing many computations to be explored simultaneously. Probability then determines the likelihood of obtaining the correct answer upon measurement. Far from being an obstacle, superposition becomes a resource. What once seemed like a philosophical nuisance becomes a technological advantage. Similarly, quantum communication and sensing rely on probabilistic behavior. The sensitivity of quantum systems to superposition and interference allows measurements of extraordinary precision. These applications reinforce the idea that quantum probability is not a sign of weakness, but a source of power. Nature's refusal to commit to a single outcome in advance enables new forms of control and insight. Yet even as technology embraces superposition, intuition lags behind. The human mind struggles to accept that something can meaningfully exist in multiple states at once. This struggle is not a failure of intelligence, but a consequence of evolutionary history. Our brains evolved to navigate a macroscopic world where superposition is effectively invisible. The categories we rely on were never meant to describe quantum reality. Superposition challenges us to expand those categories rather than abandon them. One way to approach this challenge is to recognize that classical definiteness may be an emergent phenomenon. When large numbers of particles interact, their superpositions become entangled with the environment. Interference effects become dispersed, and probabilities effectively collapse into stable patterns. The result is a world that appears definite and predictable. Superposition does not disappear, it becomes hidden. Probability remains, but its fluctuations average out. Certainty emerges as a statistical illusion. This emergence does not undermine the reality of superposition. On the contrary, it depends on it. The stability of the classical world arises from the same probabilistic principles that govern atoms. In this sense, classical reality is built from quantum uncertainty. The world we experience is the surface of a deeper, probabilistic structure. Superposition is not an anomaly at the foundation of physics, it is the foundation. Understanding this helps clarify why superposition and probability are so central to the paradox of Schrödinger's cat. The cat appears paradoxical because it occupies the boundary between the quantum and classical domains. At the atomic level, superposition and probability are routine. At the macroscopic level, they seem absurd. The paradox arises from trying to apply one description to both domains without explaining how they connect. Superposition and probability thus serve as a bridge between mathematics and experience, but a bridge that is still under construction. They force us to accept that reality may not conform to the demand for definite answers at all times. Instead, reality may be fundamentally plural until interaction forces a choice. This idea is unsettling, but it is also liberating. It suggests that the universe is richer and more flexible than classical certainty allows. As this keynote reaches its deeper implications, superposition and probability emerge not merely as technical tools, but as conceptual revolutions. They replace the image of a universe marching along a single track with that of a universe exploring a landscape of possibilities. Measurement does not simply reveal the path taken, it helps select it. Probability does not hide ignorance, it expresses structure. This perspective invites a new kind of humility. It reminds us that human intuition is not the measure of reality. The world at its most fundamental level may be stranger than we expect, yet still governed by precise and discoverable rules. Superposition and probability challenge us to accept that precision does not require certainty, and that understanding does not always mean knowing what will happen next. In the end, the third keynote reveals why quantum physics feels so different from classical physics. It is not because it is less exact, but because it is exact in a different way. Superposition allows multiple realities to coexist mathematically. Probability governs their expression in experience. Together, they redefine what it means to describe nature. They do not remove mystery, they relocate it, and in doing so, they lay the groundwork for every deeper question raised by Schrödinger's cat and by quantum mechanics as a whole. The role of the observer in measuring reality is one of the most radical and misunderstood ideas introduced by quantum physics, because it challenges the long-standing assumption that the world exists in a definite state independent of being observed. In classical physics, observation is passive. A thermometer measures temperature without changing it in any essential way. A ruler measures length without affecting the object being measured. Reality is assumed to be fully formed, and measurement simply reveals properties that already exist. Quantum mechanics disrupts this comfortable separation between observer and observed. At the quantum level, measurement is not a neutral act, it is an interaction, and that interaction fundamentally alters the system being measured. Before observation, a quantum system is described by a wave function representing a range of possible outcomes. When a measurement occurs, the system is found in one definite state. This sudden transition from many possibilities to a single outcome is not explained by the same laws that govern the system's smooth evolution beforehand. The observer, or more precisely the act of measurement, appears to play a decisive role in shaping reality as it is experienced. This does not mean that human consciousness magically creates reality, a common misunderstanding. Quantum mechanics does not require a thinking mind to collapse the wave function. What it requires is an interaction capable of producing a definite, recordable outcome. A measuring device, a photographic plate, or even the environment itself can serve this role. However, the fact that observation has this power forces a reevaluation of what it means to say that something exists before it is measured. In classical thinking, properties like position, momentum, and energy are assumed to belong to an object at all times. In quantum mechanics, these properties become relational. They acquire definite values only in the context of a specific measurement. Asking where a particle is before it is measured is not like asking where a hidden object lies behind a curtain. Instead, it is asking a question that the theory itself does not answer with a single value. The observer does not merely uncover reality. The observer helps define which aspect of reality becomes actual. This shift has profound philosophical implications. It suggests that reality at the quantum level is not a fixed stage on which events unfold, but a dynamic process in which outcomes are brought into being through interaction. The observer is part of that process, not an external spectator. This idea feels deeply unsettling because it blurs the boundary between subject and object, a boundary that classical science worked hard to enforce. The discomfort becomes especially clear in thought experiments like Schrödinger's cat. Before the box is opened, the system is described as a superposition of states. The act of opening the box is an observation that produces a definite outcome. The cat is seen as alive or dead. The troubling question is whether the cat had a definite state before the observation, or whether that state only became real when observed. Quantum mechanics, at least in its standard formulation, does not give a clear answer. It tells us how to calculate probabilities, not how to describe unobserved reality. This ambiguity has led to intense debates about the meaning of observation. Some interpretations argue that the wave function represents knowledge, not reality. In this view, observation updates information rather than creating outcomes. The system always has definite properties. The observer simply learns them. Other interpretations take the wave function more seriously, treating it as a real physical entity. In those views, observation genuinely changes the state of the system, not just the observer's knowledge. What makes the role of the observer so difficult to pin down is that observers are themselves physical systems. A measuring device is made of atoms. A human observer is a complex biological system obeying the same physical laws as everything else. If quantum mechanics applies universally, then observers should also be described by wave functions. This leads to an apparent infinite regress. Who observes the observer? At what point does a definite outcome truly occur? This problem reveals a deeper tension within quantum theory. On one hand, the theory describes the evolution of systems with exquisite precision. On the other hand, it relies on a special process, measurement, that sits outside that evolution. The observer marks the boundary between these two regimes. Yet that boundary is not clearly defined by the theory itself. It is imposed from the outside, based on practical considerations rather than fundamental principles. Modern developments such as decoherence have clarified part of this mystery. Interactions with the environment cause quantum systems to lose their ability to exhibit interference between different states. As a result, superpositions become effectively unobservable and systems appear to settle into definite outcomes. In this framework, the observer is no longer special. Any interaction with the environment can play the role traditionally assigned to measurement. Reality appears classical because it is constantly being monitored by its surroundings. However, decoherence does not fully remove the observer from the story. It explains why certain outcomes become stable and why alternatives are suppressed, but it does not explain why one particular outcome is experienced. The question of why this result rather than that one remains unanswered. The observer still occupies a privileged position, not because of consciousness, but because observation is where probabilities meet experience. The role of the observer also reshapes how truth is understood. In classical science, truth is correspondence between description and reality. In quantum science, truth becomes contextual. Statements about a system are meaningful only relative to specific measurements. Saying that a particle has a particular position without specifying how it was measured is incomplete. Reality is not described by a single, all-encompassing picture, but by a network of consistent descriptions tied to different observational contexts. This does not mean that reality is subjective or arbitrary. Quantum mechanics places strict limits on what can be observed and how observations relate to one another. Different observers performing compatible measurements will agree on their results. Objectivity is preserved, but it is redefined. It arises from shared experimental contexts rather than from an observer-independent set of properties. The observer's role also forces a reconsideration of the relationship between knowledge and existence. In the quantum framework, knowing and being are more tightly connected than in classical physics. Measurement creates a record, and that record becomes part of the physical world. Observation is an act that leaves traces, and those traces shape future possibilities. Reality is not merely revealed, it is continuously updated through interaction. This perspective aligns with the idea that physics is not just about what exists, but about what can be said to exist. The observer defines the questions that can be meaningfully asked and the answers that can be obtained. Quantum mechanics does not describe a universe frozen in a single, objective state. It describes a universe where facts emerge through processes of interaction and observation. In the end, the role of the observer in quantum measurement does not diminish reality. It enriches it. It shows that reality is not a static collection of properties, but an evolving structure shaped by relationships. The observer is not the creator of the universe, but neither is the observer irrelevant. Observation is where the abstract mathematics of probability becomes the concrete experience of facts. This insight is one of the most challenging legacies of quantum physics. It demands a shift from seeing the universe as a finished object to seeing it as an unfolding process. The observer stands at the intersection of possibility and actuality, where potential becomes real. Whether this role reflects a fundamental feature of nature or a limitation of current theory remains an open question. What is clear is that quantum physics has permanently changed how observation itself is understood, turning it from a passive act into a central element of physical reality. The clash between common sense and microscopic laws becomes most apparent when quantum physics is compared with the way humans naturally understand the world. Common sense is built from everyday experience. Objects are solid, events follow clear sequences, and causes produce predictable effects. A glass falls and breaks, fire burns, and time moves forward smoothly. These patterns are reinforced from childhood, shaping intuition so deeply that they feel self-evident. For centuries, classical physics aligned perfectly with this intuition, strengthening the belief that reality itself must operate according to these familiar rules. Quantum physics disrupts this alignment. At microscopic scales, particles do not behave like tiny versions of everyday objects. They do not travel along single, well-defined paths. They do not always have precise positions or speeds. They can pass through barriers, exist in multiple states at once, and influence one another across distances without direct contact. None of this fits comfortably within common sense. The problem is not that quantum mechanics is illogical, but that its logic is fundamentally different from the logic shaped by human scale experience. This clash arises because common sense evolved as a survival tool, not as a guide to fundamental reality. Human perception and reasoning developed to navigate a world of rocks, predators, and tools, not electrons and atoms. At those scales, quantum effects average out and disappear from direct experience. Objects appear stable because trillions of quantum interactions combine into predictable patterns. The brain therefore learns rules that work exceptionally well at macroscopic scales, but fail completely when applied to the microscopic domain. One of the strongest points of conflict involves the idea of definiteness. Common sense insists that things are always one way or another. A door is either open or closed. A sound is either present or absent. Quantum mechanics violates this expectation by allowing superposition, where a system can exist in multiple mutually exclusive states at once. This is not uncertainty in the everyday sense, but a genuine coexistence of possibilities. To common sense, this feels like a contradiction, yet at the microscopic level, it is a precisely defined physical condition. Another major clash concerns motion and location. Common sense assumes continuity. Objects move smoothly through space, passing through every intermediate position. Quantum particles do not always behave this way. They can appear to jump between states, and in some contexts, the very idea of a continuous trajectory loses meaning. Asking where a particle is between measurements may not have a clear answer. This deeply offends classical intuition, which assumes that motion must always be traceable. Causality also becomes strained under quantum laws. In everyday reasoning, causes precede effects in a clear chain. If something happens, there is a reason it had to happen that way. Quantum mechanics replaces this certainty with probability. Causes no longer guarantee outcomes, they shape likelihoods. A radioactive atom may decay now or later with no deeper cause determining the exact moment. To common sense, this feels incomplete or unsatisfying, as if nature were withholding information. To quantum theory, it is simply how reality works. The clash intensifies when microscopic laws are applied to macroscopic objects through logical extension. Schrödinger's cat is disturbing precisely because it forces common sense into conflict with quantum logic. A cat cannot be both alive and dead in ordinary understanding. Life and death are absolute categories tied to biological reality. Quantum mechanics, however, does not recognize these categories as fundamental. When the mathematics is applied consistently, the result contradicts everyday reasoning. The discomfort reveals not a failure of the theory, but the limits of common sense. This conflict often leads to resistance. Many people, including scientists, instinctively assume that microscopic laws must somehow give way to common sense at larger scales. The expectation is that there must be a hidden boundary where quantum weirdness stops and classical normality begins. Yet decades of research have shown that no sharp boundary exists. The difference is one of degree, not kind. Quantum behavior fades gradually as systems interact with their environment, but it never truly disappears. The persistence of common sense creates a psychological barrier to accepting quantum explanations. Even when equations are trusted and experiments are successful, intuition lags behind. Physicists often learn to calculate correctly while suspending the need for intuitive understanding. This divide between calculation and comprehension is rare in classical physics, but common in quantum mechanics. The theory works even when it does not feel reasonable. This tension also highlights the role of language. Everyday language is built around classical assumptions. Words like is, has, and happens imply definiteness. Quantum mechanics often requires statements that resist these grammatical structures. A particle does not simply have a position, it has a probability distribution of positions. Translating this into ordinary speech produces confusion and paradox. Common sense expects language to mirror reality directly, but quantum physics shows that language itself can become inadequate. Importantly, the clash between common sense and microscopic laws does not mean that common sense is wrong. It means that it is limited. Common sense remains extraordinarily effective within its domain. Bridges stand, machines work, and planets orbit because classical approximations hold true at large scales. Quantum mechanics does not replace common sense. It explains why common sense works where it does and why it fails where it does not. This realization shifts the goal of understanding. Instead of forcing quantum physics to conform to intuition, intuition must be expanded. This expansion is uncomfortable because it requires accepting that reality is not obligated to be intuitive. History shows similar moments of discomfort. The idea that Earth moves around the sun violated common sense. The idea that time slows down at high speeds defied intuition. Yet both turned out to be accurate descriptions of nature. Quantum mechanics represents a continuation of this pattern. The clash also reshapes the notion of realism. Common sense realism assumes that objects have properties independent of observation. Quantum mechanics complicates this assumption without completely rejecting it. Properties exist, but not always in the way common sense expects. They may be relational context dependent or probabilistic. Reality is still real, but it is not composed of neatly packaged facts waiting to be revealed. At its deepest level, the conflict between common sense and microscopic laws serves as a warning. It reminds us that intuition is not a reliable guide to fundamental truth. Nature does not scale smoothly from human experience down to its smallest components. The rules that govern atoms are not miniature versions of the rules that govern everyday objects. They are different rules that produce familiar behavior only in special circumstances. This clash is not a flaw in science, but a sign of its progress. It marks the point where understanding moves beyond comfort. Quantum mechanics forces humanity to confront a universe that is stranger, more subtle, and more flexible than common sense allows. The challenge is not to make the microscopic world sensible in everyday terms, but to accept that common sense itself is a product of deeper laws that do not share its assumptions. In the end, the clash between common sense and microscopic laws teaches humility. It shows that human perception captures only a narrow slice of reality. Beneath that slice lies a world governed by principles that resist intuition but obey precise mathematical order. Accepting this does not diminish the value of common sense, it places it in context. Common sense describes how the world appears. Quantum physics reveals how the world actually works beneath that appearance. The idea that the cat was never meant to be real is essential to understanding why Schrödinger's cat remains so widely misunderstood. The image of a half-alive, half-dead animal has become a cultural symbol. But this image was never intended to describe a physical situation that could actually occur. Schrödinger did not propose the cat as a literal prediction of quantum mechanics. He introduced it as a conceptual device, designed to expose a problem in how the theory was being interpreted. The cat was a thought tool, not an experimental proposal. At the time Schrödinger introduced the paradox, quantum mechanics was already mathematically successful but philosophically unsettled. Many physicists were content to use the equations without worrying about their meaning. Schrödinger was not. He believed that a physical theory should describe reality in a coherent way, not merely generate correct predictions. The cat was his way of showing that something had gone wrong at the level of interpretation. If the accepted view implied that a macroscopic object could exist in a grotesque superposition of life and death, then that view demanded serious scrutiny. The exaggeration in the thought experiment was deliberate. Schrödinger chose a cat precisely because it is a familiar, living creature. Life and death are absolute categories in everyday understanding. By linking these categories to a quantum event, Schrödinger forced the implications of the theory into the open. The absurdity of the conclusion was meant to be felt, not dismissed. It was a rhetorical strategy aimed at provoking reflection rather than acceptance. This intent is often lost in popular retellings. Over time, Schrödinger's cat has been portrayed as an example of how strange quantum mechanics is, rather than as a critique of that strangeness. The cat is sometimes described as if quantum theory truly predicts such bizarre states in the real world. This reverses Schrödinger's original point. He was not celebrating quantum weirdness, he was questioning whether it had been properly understood. The phrase, "the cat was never meant to be real," captures this reversal. Schrödinger did not believe that cats, or any macroscopic objects, genuinely exist in superpositions of mutually exclusive states. He believed that the quantum formalism, when naively extended to large systems, produced conclusions that clashed with physical intuition and biological reality. The paradox was intended to show that the theory required either a clearer boundary between quantum and classical domains, or a deeper reinterpretation of what the wave function represents. This distinction matters because it highlights the difference between mathematical description and physical reality. Quantum mechanics describes systems using abstract mathematical objects. These objects can be manipulated and extended logically, but not every mathematical possibility corresponds to a physically meaningful situation. Schrödinger worried that treating the wave function as a literal description of reality at all scales blurred this distinction. The cat paradox was a way of testing whether such literalism made sense. The fact that the cat is not real also underscores the role of thought experiments in science. Thought experiments are not predictions, they are probes. They test the internal consistency of ideas and expose hidden assumptions. Schrödinger's cat probes the assumption that quantum superposition applies universally without modification. By pushing this assumption to an extreme, the thought experiment reveals its consequences. Whether those consequences are acceptable is a matter for interpretation and further theory, not for immediate belief. Understanding that the cat was never meant to be real also clarifies why the paradox remains unresolved. There is no single solution because the problem it raises is not empirical but conceptual. Different interpretations of quantum mechanics resolve the paradox in different ways, not by changing the mathematics, but by changing what the mathematics is taken to mean. Some interpretations deny the physical reality of the superposition at the macroscopic level. Others accept it and modify their understanding of reality itself. The cat remains imaginary because it sits at the crossroads of these choices. The unreality of the cat also reveals something about the limits of visualization. Schrödinger chose an image that resists visualization on purpose. A cat that is both alive and dead cannot be pictured coherently. This failure of imagination is not accidental. It signals that classical imagery breaks down when applied to quantum concepts. The paradox forces us to recognize that some aspects of quantum theory may not be representable in familiar visual terms. This insight protects against a common mistake, taking metaphors too literally. Quantum mechanics often relies on metaphors drawn from classical physics, such as waves and particles. These metaphors are useful but incomplete. Schrödinger's cat is itself a metaphor, not a model. Treating it as a literal scenario leads to confusion. Recognizing it as a metaphor restores its proper function as a critical tool. The idea that the cat was never meant to be real also emphasizes Schrödinger's philosophical stance. He was deeply uneasy with interpretations that treated observation as creating reality. He preferred to believe that the world exists in a definite state independent of measurement. The cat paradox was his way of arguing that the prevailing interpretation had gone too far in abandoning this realism. By showing that it led to absurd conclusions, he hoped to motivate a return to a more coherent picture. Ironically, the continued fame of the cat suggests that Schrödinger's strategy succeeded, but not in the way he expected. Rather than rejecting the problematic interpretation, physicists embraced the paradox as a defining feature of quantum theory. The cat became a symbol of unresolved questions rather than a reason to abandon the theory. This outcome reflects the extraordinary empirical success of quantum mechanics. When a theory works so well, its conceptual difficulties are tolerated rather than eliminated. The unreality of the cat also helps explain why modern physics does not attempt to build such an experiment. No one seriously proposes placing a living cat in a quantum superposition. The practical difficulties alone are overwhelming. More importantly, doing so would miss the point. The value of the paradox lies in what it reveals about theory, not in what it predicts about experiments. In contemporary discussions, the phrase, "the cat is not real," serves as a reminder to distinguish between physical claims and interpretive puzzles. Quantum mechanics does not assert that macroscopic objects behave in absurd ways. It asserts a mathematical framework whose interpretation remains open. The cat illustrates the tension within that framework, not a literal description of the world. Ultimately, understanding that the cat was never meant to be real allows the paradox to be appreciated in its proper light. It is not a story about animals trapped in impossible states. It is a story about the limits of theory, the dangers of unexamined assumptions, and the power of imagination to reveal conceptual flaws. Schrödinger's cat survives precisely because it is not real. Its unreality gives it the freedom to challenge our understanding without being constrained by experimental practicality. The enduring lesson is that science advances not only through new data, but through critical reflection on existing ideas. Schrödinger's cat exemplifies this process. By imagining something that should not exist, Schrödinger forced physicists to ask why their theory seemed to allow it. The cat's purpose was never to live or die, but to provoke thought. In that role, it remains profoundly real, even though the cat itself never was. The lasting influence of Schrödinger's cat lies not in the image of the cat itself, but in how the idea continues to shape modern physics and philosophy. What began as a critical thought experiment has become a central reference point for discussions about the nature of reality, measurement, and knowledge. Its endurance reflects the fact that the questions it raises have not been settled. Instead, they have deepened, branching into new areas of research and thought as science has progressed. In modern physics, the legacy of the cat is most visible in the ongoing study of quantum foundations. Physicists continue to ask what the mathematical formalism of quantum mechanics actually represents. Does the wave function describe physical reality, or does it represent information about potential measurement outcomes? Schrödinger's cat remains a touchstone in this debate because it dramatizes the consequences of each answer. If the wave function is real, then superpositions must somehow extend to macroscopic systems. If it is merely informational, then the task becomes explaining why information evolves according to strict physical laws. The paradox has also influenced how physicists think about the measurement problem. Measurement is no longer treated as a simple technical step, but as a fundamental process requiring explanation. Research into decoherence, for example, was motivated in part by the desire to understand why quantum superpositions are not observed at large scales. Decoherence shows how interactions with the environment suppress interference between different quantum states, making the world appear classical. While this does not solve every interpretive issue, it has clarified the transition from quantum possibility to classical appearance, directly addressing the tension highlighted by Schrödinger's cat. The cat's influence extends into experimental physics as well. Advances in technology have made it possible to create and observe superpositions in increasingly large systems. Scientists have placed molecules containing thousands of atoms into quantum superpositions and observed interference effects. Each such experiment echoes the logic of Schrödinger's cat, testing how far quantum behavior can be extended before classical behavior takes over. Although no living creatures are involved, these experiments bring the paradox closer to empirical investigation. In the field of quantum information, Schrödinger's cat has found a new interpretation. Set states now refer to specific quantum superpositions used in quantum computing and communication. These states exploit the same principles of superposition and coherence that underlie the original paradox. What was once a conceptual problem has become a practical resource. The cat has moved from philosophy into engineering, demonstrating how foundational questions can lead to technological innovation. Philosophically, the cat has reshaped discussions about realism and objectivity. Classical philosophy assumed that the world has a definite structure independent of observation. Quantum mechanics complicates this assumption, and Schrödinger's cat makes the complication impossible to ignore. Philosophers now debate whether reality is fundamentally observer-independent or whether observation plays a constitutive role. These debates draw on the cat paradox to illustrate the stakes of different positions. The paradox has also influenced how philosophers think about probability. In classical contexts, probability reflects ignorance. In quantum contexts, probability appears to be built into reality itself. Schrödinger's cat highlights this difference by forcing probability into a domain where ignorance seems implausible. Either the cat is alive or dead, yet quantum mechanics describes a probability until observation. This tension has inspired new philosophical accounts of probability, causation, and chance. Another lasting impact of the cat is its role in shaping scientific humility. The paradox reminds scientists that predictive success does not guarantee conceptual clarity. Quantum mechanics works extraordinarily well, yet its meaning remains contested. This recognition encourages openness to new interpretations and even new theories. Schrödinger's cat stands as a caution against assuming that current frameworks are final. The idea has also had a profound effect on education and communication. Schrödinger's cat is often one of the first quantum concepts introduced to students and the public. Its vividness makes abstract ideas approachable. While this accessibility comes with the risk of oversimplification, it also fosters curiosity. Many people encounter quantum physics for the first time through the cat, making it a gateway to deeper inquiry. Culturally, the cat has transcended science. It appears in literature, film, and art as a symbol of ambiguity and uncertainty. This cultural presence reflects the broader influence of quantum ideas on how modern society thinks about knowledge and reality. The cat has become shorthand for situations where outcomes are indeterminate until a choice is made or information is revealed. In this way, a scientific thought experiment has shaped metaphors used far beyond physics. In philosophy of mind, the cat paradox has even been invoked in discussions about consciousness. While most physicists reject the idea that consciousness plays a special role in quantum measurement, the paradox has kept such questions alive. It has forced careful distinctions between observation, awareness, and physical interaction. These discussions have clarified what quantum mechanics does and does not imply about the mind's role in reality. The endurance of Schrödinger's cat also reflects a broader shift in how science approaches fundamental questions. Modern physics increasingly recognizes that understanding may require multiple layers of description. Classical and quantum accounts may both be valid within their domains, even if they rest on different assumptions. The cat symbolizes the tension between these layers and the challenge of reconciling them. Perhaps the most important influence of the cat is its role in keeping foundational questions active. In a field driven by technical progress, it is easy for philosophical issues to be sidelined. Schrödinger's cat resists this sidelining. It continually reappears in discussions, reminding physicists that interpretation matters. It ensures that questions about reality, measurement, and meaning remain part of scientific discourse. Looking forward, the ideas associated with Schrödinger's cat are likely to become even more relevant. As quantum technologies advance and quantum systems become more integrated into everyday devices, the boundary between microscopic and macroscopic will blur further. Understanding how quantum principles give rise to classical experience will be essential not only for philosophy, but for practical applications. The cat paradox provides a conceptual framework for thinking about this transition. In the end, the story of Schrödinger's cat is a story about the power of ideas to outlive their original purpose. What began as a critique has become a cornerstone. It continues to inspire research, provoke debate, and challenge assumptions. The cat itself may never have been meant to be real, but its influence certainly is. By forcing us to confront the deepest questions about how the world works and how we know it works, Schrödinger's cat has secured a permanent place in the intellectual landscape of modern science and philosophy.